Another reaction that is very important in identifying the identity of the alcohol is oxidation. So through this reaction, you can know if you're starting with a primary, secondary, or a tertiary alcohol. In this reaction, we use oxidizing agents, and the process is called oxidation. Oxidation is a process where you either lose hydrogens or you gain oxygens. And with these types of reactions, we have different products based on the type of oxidizing agent that we are using. But in all of the cases, what we are doing here is that we are actually losing hydrogens. This is what we are. So all what you need to do is just locate the carbon that is connected to the OH. And the rule says for these reactions is that the OH will lose a hydrogen. So you will lose a hydrogen from the OH, and you will lose a hydrogen from the carbon as well. So two things to lose, two sigma bonds. You're going to lose the sigma bond between the carbon and the hydrogen, and you're going to lose the sigma bond between the oxygen and the hydrogen. And remember, when you lose two sigma bonds, you're going to form a pi bond. So our product in these types of reactions is going to be a carbon double bond O, which is a carbonyl. So the product here is going to be a carbonyl product. So for this reaction to happen, the carbon needs to have a hydrogen to lose. So I need to be working with a primary or a secondary alcohol. I cannot be working with a tertiary alcohol because tertiary alcohol has no hydrogen here. So I would need to lose a hydrogen from the carbon, and I would need to lose a hydrogen from the OH in order to carry this reaction. Now, there are different carbonyls that form based on the type of oxidizing agent that I use and the type and the identity of the alcohol that I start with. So I can form three types of carbonyls. I can form an aldehyde, a ketone, or a carboxylic acid, depending on the strength of the oxidizing agent and the identity of the alcohol. So let's start with the types of the oxidizing agents. There are two types, strong and mild. Let's start with the strong. For strong oxidizing agent in there, these are water soluble. You don't have to memorize them, but just know that these are water soluble. So whenever you see chromium in there, CRs are oxidizing agents, and what makes them strong is the solubility, is the water solvent that they are accompanied with. This is sodium dichromate in presence of an acid and water. This is one type of a strong oxidizing agent. Another one is the chromic acid. This H2CrO3, it's a chromic acid. It's the same thing. You have chromium that is an acid. This means that it is dissolved in water. We call this a Jones reagent or chromic acid. Any one of those, if they are present, these are considered to be strong oxidizing agents. And the rule says that strong oxidizing agents normally have different products based on the type of the alcohol that you are working with. If you start with a strong oxidizing agent and the primary alcohol, your product is an acid. And if you start with a strong oxidizing agent and the secondary alcohol, your product is a ketone. So the reaction will go as such in there. This is how you write your reagents. This is sodium dichromate. It's a strong oxidizing agent. You can write the H2SO4 and water all the way next to the sodium dichromate, or you can write them underneath the arrow. It doesn't matter. What matters is that you need to know what type of alcohol you are starting with to see if you're going to get a carboxylic acid or you're going to get a ketone. So if you're starting with a primary alcohol in there, this is what's going to happen. Okay, with the primary alcohol, the reaction is carried over two steps. And in order to figure out the product in this case, what you need to do is that you need to locate the carbon that is connected to the OH in there. And once you figure out that, this is going to be your reactive site. So that carbon is going to be your reaction or reactive site in there. The rule says that the carbon is going to lose a hydrogen. Here I do have two hydrogens. So the carbon is going to lose a hydrogen and the OH is going to lose a hydrogen on that same carbon. Okay, so we're going to end up is an intermediate. That's why I said the reaction happens over two steps in there. So I'm going to end up getting an intermediate in there, and the intermediate is going to be my aldehyde, but the reaction will not stop. So here you go. I'm going to end up getting my aldehyde. I'm still having an oxygen in there, and whatever hydrogen is left here, it is there. Okay, so that is going to be my aldehyde. I'm using a strong oxidizing agent, and that is going to eliminate any hydrogen in its way. First step, as I said, the oxidizing agent is going to take a hydrogen from the carbon and then a hydrogen from the OH and create a carbonyl over here, which is the aldehyde. And we're going to call this aldehyde intermediate. So this one is an intermediate. However, because as I said that the oxidizing agent is so strong, the sodium dicarbonate is so strong, sodium dichromate is so strong in there, the reaction does not stop here. So the reaction is going to continue, and this hydrogen is going to get oxidized further, and that hydrogen is going to change into a carboxylic acid. So that hydrogen is going to be an OH, and my product is going to be a carboxylic acid in this case. So the hydrogen will change into an OH. So back up there, if I want to draw the product right away, I am not adding any of the carbons. So I have a benzene and I have two carbons next to it. So I just draw a benzene and draw those two carbons in there. And see the carbon of the alcohol. This is an alcohol. It's a primary alcohol. So that carbon of the alcohol in there, it's going to turn into a carboxylic acid. So that carbon, I'm just going to go ahead and turn it into a carboxylic acid. I am not adding any carbons. I have two carbons on the benzene. I have two carbons over here. And my product is going to be a carboxylic acid. Okay, let's have another example. In there. Then the other example over here is something like this. So let's say if I have this like that with an OH. Same thing. And I am using a strong oxidizing agent, which is the sodium dichromate, O7, in presence of an acid and water. Okay, same idea in there. So I'm just going to locate my carbon with the OH. I know that this one is a primary alcohol. It's so important to know the type of alcohol that you are working with, because I know primary alcohols with a strong oxidizing agent. Oxidizing agents, normally I represent them by an O and the brackets like this. So primary alcohols and strong oxidizing agents will give me carboxylic acid in there. They won't give me aldehyde. They will go all the way and oxidize to carboxylic acid. So I am going to locate that carbon, and this carbon, I'm going to change it into a carboxylic acid. Keep the same number of carbons that you have, the same format that you have. So I'm starting with an isopropyl in there, and then I do have a carbon next to the isopropyl, and then I have another carbon. Now on this carbon, I'm going to do a double bond in there and an OH. Okay, see what I did? On that carbon here, I'm going to change the alcohol into an acid. I did not add any single carbon, any additional carbon in there. So again, primary alcohols, strong oxidizing agent, your product is a carboxylic acid. For secondary alcohols. Now, for secondary alcohols, the oxidation happens as was explained earlier, that when you're doing the oxidation, always in oxidation, you're losing the hydrogen on the carbon, the hydrogen on the OH. That's it. You don't have any additional hydrogen to lose over here. So there is no way you're going to get an aldehyde as an intermediate. This here happens in one step, and you're going to get only one product, which is the ketone in this case. So with an oxidizing agent, here it's a strong oxidizing agent, your product is going to be a ketone, and there will be no further oxidation of the ketone. Here I had an aldehyde, so I could do oxidation and change the hydrogen into an OH. But here I have no further hydrogen to oxidize, so I'm going to end up getting my ketone. So again, back here, if you're using a strong oxidizing agent, secondary alcohols always are oxidized into ketones. This is one type of oxidizing agent, which is strong. Now for the mild one. The mild one, it means it's less strong. And the mild one is the PCC in presence of dichloromethane. PCC is pyridinium chlorochromate. So PCC, the agent, stands for pyridinium chlorochromate, and pyridinium chlorochromate still have the chromium in it, but the solvent that you are using is not water. This is an organic solvent, which is dichloromethane. So that is going to decrease the reactivity of that oxidizing agent in there. And this is why we say pyridinium chlorochromate is less reactive than the sodium dichromate, because this one is dissolved in organic solvent. The sodium dichromate is dissolved in water. Okay, so this one is going to oxidize the primary alcohol and stop it at its intermediate, which is the aldehyde. So the reaction goes with the mild oxidizing agent, you get your intermediate and you stop at the intermediate. You don't continue to the further oxidation to that aldehyde into an acid. It's as simple as that. So with the primary alcohols, again, we're going to locate our carbon that has the OH in there, and the oxidation happens by simply taking out the hydrogen. So we're going to take the hydrogen on the carbon, we're going to take the hydrogen on the oxygen, and we are going to end up getting the aldehyde. Why the aldehyde? Because this one has a hydrogen in there and the hydrogen stays. So I'm going to lose a hydrogen from the carbon. I'm going to lose the hydrogen from the OH in there. Again, I am not adding a single carbon. Whatever carbons I have, I'm just going to add them in the product in there and then create a double bond where my OH was. So my OH was here, so I'm just going to go ahead and create a double bond. I still have this hydrogen that is left, so that hydrogen is going to be over here. And that is going to be my aldehyde. Now it's going to be a product because this guy is mild. PCC is mild, it is not strong, so it doesn't have the power to continue the oxidation and oxidize this hydrogen into an OH, so you're going to stop at the aldehyde. Any primary alcohol will be oxidized into an aldehyde with a mild oxidizing agent. Doesn't matter what type, any primary alcohol. So this is why for these reactions it's very important to know what type of alcohol you're starting with, to know what type of product you are going to get. So this is again a primary alcohol in there. So this is going to be the carbon here in the OH. So I am going to lose, these are my two hydrogens. So I'm going to lose a hydrogen here and an OH there. And I'm going to end up getting an aldehyde. I have one carbon, I'm just going to keep it one carbon there. But the OH, the COH is going to turn into a carbonyl. And then I'm going to end up having leftover hydrogen over here. So that hydrogen will be there. Here you go. And that is going to be your aldehyde product as well. For the secondary alcohol, same idea. Actually, with secondary alcohols, it doesn't matter if it's a strong or mild oxidizing agent. because you don't have any further hydrogen to oxidize. So you're always going to end up getting a ketone, no matter what you do. So over here on this carbon, I'm going to lose the hydrogen carbon on the carbon. I'm going to lose the hydrogen on the oxygen in there. And I am going to form a carbonyl here. Notice I am not adding any carbons. I am using the carbon of the cycle, so this means that the double bond is going to be here, and then I'm going to end up getting my oxygen, and that is going to be the ketone. So oxidation of secondary alcohols, whether I am using strong or mild oxidizing agent, will give me always a ketone. And the same thing, this is a secondary alcohol. So what I have here is a hydrogen on this oxygen. So I'm going to end up losing this hydrogen. I'm going to end up losing the hydrogen on the OH and creating a double bond between the carbon and the oxygen. And my product is going to simply look like this. Don't forget the CH3, and that is going to be my ketone. You can write the summary on the cheat sheet if you like in there and bring it to the exam. You cannot write any reactions, but you can write this one. These are the conditions of the reaction. So when you are working with a primary alcohol, you have two products, either the aldehyde or the acid form. You can go straight to the acid if you use a strong oxidizing agent. If you use mild oxidizing agent, you're going to get to the aldehyde. But if you have an aldehyde, you can oxidize to carboxylic acid by using any of these mild or strong oxidizing agents. Secondary alcohol, it doesn't matter. You get a ketone, but tertiary alcohols, because you don't have a hydrogen on the carbon. So look, this carbon over here does not have any hydrogens. So that carbon there is missing a hydrogen. There is no hydrogen here. So if there is no hydrogen here, you cannot perform the oxidation as you should, because the rule for the oxidation to take out the hydrogen from the carbon and the hydrogen from the oxygen and create a double bond. No hydrogen here, you cannot make a 5-bond carbon. So this is why there will be no reaction. Any tertiary alcohol that you start with, so this is a tertiary alcohol here. That one is also a tertiary alcohol. So any tertiary alcohol that you are starting with, again, has no hydrogen here. So this means that it will end up having no reaction. The last reaction is the reaction of phenols. This is an acid-base reaction. And with these types of reactions, phenol is going to behave as a weak acid. So it's going to behave an acid from its hydrogen in there. And from the first part of the course, which is the 111, bases are two types. We know that bases are two types. Bases can either be strong or they can be weak, okay? However, in both types, bases, they are electron rich. They have lone pairs. But now, if they are strong, they are going to have a negative charge. So you know them by their negative charge. It's an ionic bond. Let's have an example. If I say sodium hydroxide, NaOH, I know that the OH has 3 lone pairs. It's a negative charge because sodium is positive. This is an ionic bond. So I know that sodium hydroxide is a strong base because of the negative charge. Same thing as potassium hydroxide. These are examples of strong bases, okay? These are examples of strong bases. Now, weak bases are neutral. They don't have a charge in there, but they have lone pairs. So notice, the basic site is the site with the lone pairs, but you know if it's strong or weak, if it's carrying a charge or not. So if it's carrying a negative charge, then this is a strong base, okay? If it is not, like for example, like methanol, for example. So methanol here, your basic site is always the lone pair site. So the oxygen is the base, but because this oxygen is a zero charge, we call it a neutral weak base. This oxygen here, this oxygen there is a negative charge, we call it a strong base. Okay, same thing for, let's say, water. Water has lone pairs on the oxygen, so your basic site is the oxygen, and it has lone pairs, but however it is a neutral, so it is going to be a weak base. And this is how you differentiate between a weak base and a strong base. This reaction, because phenols are weak acids, they require a strong base in order for them to work. They cannot work with weak bases because the acid is already weak. So here we have a case of a weak acid, a strong base, so the reaction can happen. And if this is the case, always the rule says that bases take acidic hydrogens. So always the rule says base take the acidic hydrogen. So you have your base in there, the base is going to come and take that acidic hydrogen, and you're going to create a conjugate base. So you're going to create your O negative in there, that is a conjugate base that is going to counter ion with any plus ion in the solution, and which is the sodium over here. It's this Na plus. Plus you have your conjugate acid. So the base turns into a conjugate acid. It's going to be water in this case. So you're going to end up having your conjugate base and conjugate acid. Okay, so let's have an example in there. This is an example. If we have phenols and we are reacting those with strong bases, remember what I said, bases, they take, the base here is the OH. So the bases, they take acidic hydrogens and they create a conjugate acid. This is what happens. So the base in here, which is the OH, is going to come and take the hydrogen, and you are going to make a conjugate acid and a conjugate base. So that is going to be my conjugate base because it has a negative charge. That conjugate base will be balanced by any positive charge in the solution, plus the base will turn into a conjugate acid, meaning that it's going to take its hydrogen, OH will take the hydrogen and will make water. And I'm going to end up getting my conjugate acid, and this one is going to be my conjugate base. Guys, remember that bases are negative. If I have a negative charge, then this means that it's a base and it's a strong one. Okay, your reactants are acids plus bases. Your products are conjugate acids and conjugate bases. Because this one is a weak acid, it won't work with a weak base, so there will be no reaction.